I'm going to omit a section that does arise in the text called, "Are you now or have you ever been an atomist?" And I'll read 1.3 Atoms. I was brought up to look at the atom as a nice hard fellow, red or gray in color, according to taste. Atomism. And that was a quote by Rutherford. Atomism. The Greeks have been kicked around a lot in the last couple of millennia. Dominated by the Romans, bullied during the Crusades by warlords going to and from the Holy Land, and occupied by Turkey until recently. It's no wonder they preferred to remember their salad days, when their best thinkers came up with concepts like democracy and atoms. Greece is democratic again after a period of military dictatorships, and an atom is proudly pictured on one of their coins. That's why it hurts me to have to say that the ancient Greeks' hypothesis that matter is made of atoms was pure guesswork. There was no real experimental evidence for atoms, and the 18th century revival of the atom concept by Dalton owed little to the Greeks other than the name, which means unsplittable. Subtracting even more cruelly from the Greeks' glory, the name was shown to be inappropriate in 1899, when physicist J.J. Thomson proved experimentally that atoms had even smaller things inside them which could be extracted. Thomson called them electrons. The unsplittable was splittable after all. But that's getting ahead of our story. What happened to the atom concept in the intervening 2,000 years? Educated people continued to discuss the idea, and those who were in favor of it could often use it to give plausible explanations for various facts and phenomena. One fact that was readily explained was conservation of mass. For example, if you mix 1 kilogram of water with 1 kilogram of dirt, you get exactly 2 kilograms of mud, no more, no less. The same is true for the variety of processes, such as freezing of water, fermenting beer, or pulverizing sandstone. If you believe in atoms, conservation of mass made perfect sense, because all these processes could be interpreted as mixing and rearranging atoms, without changing the total number of atoms. Still, this is nothing like a proof that atoms exist. If atoms did exist, what types of atoms were there? And what distinguished the different types from each other? Was it their sizes, their shapes, their weights, or even some other quality? The chasm between the ancient and modern atomisms became evident when we consider the wild speculations that existed on these issues until the present century. The ancients decided that there were 4 types of atoms: earth, water, air, and fire. The most popular view was that they were distinguished by their shapes. Water atoms were spherical, hence water's ability to flow smoothly. Fire atoms were sharp points, which was why fire hurt when it touched one's skin. There was no concept of temperature until thousands of years later. The drastically different modern understanding of the structure of atoms was achieved in the course of the revolutionary decade stretching 1895 to 1905. The main purpose of chapters 1 and 2 is to describe those momentous experiments. Atoms, light, and everything else. Although I tend to ridicule the ancient Greek philosophers, like Aristotle, let's take a moment to praise him for something. If you read Aristotle's writing on physics, or just skim them, which is all I've done, the most striking thing is how careful he is about classifying phenomena and analyzing relationships among phenomena. The human brain seems to naturally make a distinction between 2 types of physical phenomena: objects and motion of objects. When a phenomenon occurs, that does not immediately present itself as one of these. There is a strong tendency to conceptualize it as one or the other, or even to ignore the existence completely. For instance, physics teachers shudder at students' statements that the dynamite exploded and force came out of it in all directions. In these examples, the non-material concept of force is being mentally categorized as if it was a physical substance. The statement that winding the clock stores motion in the spring is a miscategorization of potential energy as a form of motion. An example of ignoring the existence of phenomenon altogether can be elicited by asking people why we need lamps. The typical response that the lamp illuminates the room so we can see things ignores the necessary role of light coming into our eyes from the things being illuminated. If you ask someone to tell you briefly about atoms, the likely response is that everything is made of atoms. But we've now seen that it's far from obvious which everything this statement would properly refer to. For the scientists of the early 1900s who were trying to investigate atoms, this was not a trivial issue of definitions. There was a new gizmo called the vacuum tube, of which the only familiar example today is the picture tube of a TV. In short order, electrical tinkerers had discovered a whole flock of new phenomena that occurred in and around vacuum tubes, and it was given them picturesque names like X-rays, cathode rays, Hertzian waves, and N-rays. These were the types of observations that ended up telling us that we know about matter, but fierce controversies ensued over whether these were themselves forms of matter. Let's bring ourselves up to the level of classification of phenomena employed by physicists in the year 1900. They recognized three categories. First, matter has mass, can have kinetic energy, and can travel through a vacuum, transporting its mass and kinetic energy with it. Matter is conserved both in the sense of conservation of mass and conservation of the number of atoms of each element. Atoms can't occupy the same space as other atoms, so a convenient way to prove something is not a form of matter is to show that it can pass through a solid material in which the atoms are packed together closely. Light has no mass, always has energy, and can travel through a vacuum, transporting its energy with it. Two light beams can penetrate through each other and emerge from the collision without being weakened, deflected, or affected in any other way. Light can penetrate certain kinds of matter, example, glass. The third category is everything that doesn't fit the definition of light or matter. This catch-all category includes, for example, time, velocity, heat, and force. The chemical elements. How would one find out what types of atoms there were? Today, it doesn't seem like it should have been very difficult to work out an experimental program to classify the types of atoms. For each type of atom, there should be a corresponding element, i.e. a pure substance made out of nothing but the type of atom. Atoms are supposed to be unsplittable, so a substance like milk could not possibly be elemental, since churning it vigorously causes it to split up into two separate substances, butter and whey. Similarly, rust could not be an element because it can be made by combining two substances, iron and oxygen. Despite its apparent reasonableness, no such program was carried out until the 18th century. The ancients presumably did not do it because observation was not universally agreed on as the right way to answer questions about nature, and also because they lacked the necessary techniques, or the techniques were the province of laborers with low social status, such as smiths and miners. Alchemists were hindered by atomism's reputation for subversiveness and by a tendency toward mysticism and secrecy. The most celebrated challenge facing the alchemists, that of converting lead into gold, is one we now know to be impossible, since lead and gold are both elements. By 1900, however, chemists had done a reasonably good job of finding out what the elements were. They also had determined the ratios of the different atoms' masses fairly accurately. A typical technique would be to measure how many grams of sodium would combine with 1 gram of chlorine to make salt. This assumes you've already decided, based on other evidence, that salt consisted of equal numbers of sodium and chlorine atoms. The masses of individual atoms, as opposed to the mass ratios, were known only to within a few orders of magnitude based on indirect evidence, and plenty of physicists and chemists denied that individual atoms were anything more than convenient symbols. In the margin of the page to the left, there's examples of masses of atoms compared to that of hydrogen. Note how some, but not all, are close to integers. That stands to be examined a little more closely, because I'm reading right now. Making sense of the elements. What's my time here for this recording? 10 minutes and 48 seconds. Okay, I'll keep reading. Making sense of the elements. As the information accumulated, the challenge was to find a way of systematizing it. The modern scientist's aesthetic sense rebels against complication. This hodgepodge of elements was an embarrassment. One contemporary observer, William Crookes, described the elements as extending before us as stretched the wide Atlantic before the gaze of Columbus, mocking, taunting, murmuring strange riddles which no man has yet been able to solve. It wasn't long before people started recognizing that many atoms' masses were nearly integer multiples of the mass of hydrogen, the lightest element. A few excitable types began speculating that hydrogen was the basic building block, and that the heavier elements were made of clusters of hydrogen. It wasn't long, however, before the parade was rained on by more accurate measurements, which showed that not all of the elements had atomic masses that were near integer multiples of hydrogen, and even the ones that were close to being integer multiples were off by 1% or so. Chemistry professor Dmitri Mendeleev, preparing his lectures in 1869, wanted to find some way to organize his knowledge for his students to make it more understandable. He wrote the names of all the elements on cards and began arranging them in different ways on his desk, trying to find an arrangement that would make sense of the muddle. The row and column scheme he came up with is essentially our modern periodic table. The columns of the modern version represent groups of elements with similar chemical properties, and each row is more massive than the one above it. Going across each row, this almost always resulted in placing the atoms in sequence by weight as well. What made the system significant was its predictive value. There were 3 places where Mendeleev had to leave gaps in his checkerboard to keep chemically similar elements in the same column. He predicted that elements would exist to fill these gaps, and extrapolated or interpolated from other elements in the same column to predict their numerical properties such as masses, boiling points, and densities. Mendeleev's professional stock skyrocketed with his 3 elements, later named gallium, scandium, and germanium, were discovered and found to have very nearly the properties he had predicted. One thing that Mendeleev's table made clear was that mass was not the basic property and distinguished atoms of different elements. To make his table work, he had to deviate from ordering the elements strictly by mass. For instance, iodine atoms are lighter than tellurium, but Mendeleev had to put iodine after tellurium so that it would lie in a column with chemically similar elements. And scrolling back up a little bit is the periodic table. I'll just read the caption under the picture. A modern periodic table, elements in the same column have similar chemical properties. The modern atomic numbers discussed in Chapter 2 were not known in Mendeleev's time, since the table could be flipped in various ways. Okay, I'll read this last section because it'll complete it. Direct proof that atoms existed. The success of the kinetic theory of heat was taken as strong evidence that, in addition to the motion of any object as a whole, there is an invisible type of motion all around us, the random motion of atoms within each object. But many conservatives were not convinced that atoms really existed. Nobody had ever seen one, after all. It wasn't until generations after the kinetic theory of heat was developed that it was demonstrated conclusively that atoms really existed, and that they participated in continuous motion that never died out. The smoking gun to prove atoms were more than mathematical abstractions came when some old, obscure observations were re-examined by an unknown Swiss patent clerk named Albert Einstein. A botanist named Brown, using a microscope that was state-of-the-art in 1827, observed tiny grains of pollen in a drop of water on a microscope slide, and found that they jumped around randomly for no apparent reason. Wondering at first if the pollen he'd assumed to be dead was actually alive, he tried looking at particles of soot, and found that the soot particles also moved around. The same results would occur with any small grain or particle suspended in a liquid. The phenomenon came to be referred to as Brownian motion, and its existence was filed away as a quaint and thoroughly unimportant fact, really just a nuisance for the microscopist. It wasn't until 1906 that Einstein found the correct interpretation for Brown's observation. The water molecules were in continuous random motion and were colliding with the particle all the time, kicking it in random directions. After all, the millennia of speculation about atoms, at last, there was solid proof. Einstein's calculations dispelled all doubt, since he was able to make accurate predictions of things, like the average distance traveled by the particle in a certain amount of time. Einstein received the Nobel Prize not for his theory of relativity, but for his papers on Brownian motion and the photoelectric effect. Discussion questions. Based on Franklin's data, how could one estimate the size of an oil molecule? Talk about Franklin? Is it Brown? Okay, how could knowledge of the size of an individual aluminum atom be used to infer an estimate of its mass, or vice versa? C. How could one test Einstein's interpretation by observing Brownian motion at different temperatures?